Okay, so as you can see for this question, it's basically a pulley problem, but it's got a little bit of a twist to it because you've actually got a water rocket on one of the sides of the pulley. So all of a sudden it's not your boring statics problem anymore, it's actually an interesting dynamics problem. So the question's basically asking you what's the acceleration of m1 as this water rocket over here ejects water out at a velocity v0 relative to the container. We've also been told other things about this water rocket over here. Its initial mass is going to be equal to m0. So already you can start to understand that the mass of this thing isn't actually going to be constant, which is what makes this problem a little tricky. And we're told that the rate of change of the mass, right, is essentially going to be equal to r0. So in a small time dt, the tiny amount of mass dm that gets ejected out of this rocket is going to be equal to r0. So using this information, can we figure out what the acceleration of m1 is? So that's what I'm going to be showing you today. If you want to pause the video and try the problem out, then feel free to do so, and I'll solve this problem afterwards. So yeah, the way I solved this problem was to basically use the more general form of Newton's second law. So most of you probably know F equals ma, right? The net force on an object is going to be equal to the mass times its acceleration. But in this case, this equation doesn't actually cut it because it's actually assuming that the mass is constant throughout the entire process that you're trying to look at. However, in this case, as you can see, because we got a rocket, it's going to be exerting a force, but as it ejects water outwards, its mass is going to be decreasing. So we can't just use this form of Newton's second law. Another form of Newton's second law that you might also be familiar with is that the net force on the object is going to be equal to the rate of change of its momentum. So P is its momentum. And this is good because you know that momentum is equal to the mass times its velocity, which means if you differentiate that, then using product rule, you can see that you can either vary the velocity with respect to time, which just gives you the acceleration, or you can vary the mass with respect to time. So this is actually a more general form because it also accounts for the fact that the mass might change during whatever system you're looking at. So yeah, this is the law I'm going to be using to solve this problem. And in order to do that, I need to figure out what the change in momentum is going to be if we look at a tiny little time jump as this rocket travels upwards. And a good thing to do when you're doing momentum problems or you want to calculate the change in momentum is to draw a before and after diagram. So that's what I did for this problem, and I'm going to show you what I did for that. So here's the before. So since we're doing this generally, we don't want to really look at it from when it starts off at rest. We basically want to look at it as at a general time, so at a time t. So at time t, right? And then we'll look at the same situation again at a time t plus delta t, so we're looking at a tiny time step ahead. And doing before and after with that will help us get dp over here, which is the change in momentum in this tiny time interval dt. So before, what's it going to look like? Well, it's going to be kind of simple. It's just going to be equal to whatever the mass is at that point in time, which will be m2, right? m2 is actually dependent with time. It actually varies with time. And I guess its velocity is going to be acting upwards, right? And we can give that a general velocity v. Now we want to do the after situation. So after. And just to be clear over here, when we're talking about after, we're talking about at time t plus delta t plus dt over here. So we're just looking at a tiny time step ahead and seeing how the velocity will change and how the mass ejected is going to be changing as well. So now you've got that same container again, right? And I've left a little chunk out over here because it's actually going to be ejecting some of its mass downwards. So the mass of this tiny chunk in a time dt is going to be equal to dm. And its velocity is going to be acting downwards v0 relative to the container, right? So its velocity is going to be acting downwards. And this velocity, because it's relative to the velocity of the container, if the container was already moving at a speed v upwards, that means that the velocity at which the mass is ejected downwards is going to be equal to v0 minus v, right? So now we've also got to consider what the mass of the remaining bit of the rocket is. and it's going to actually have lost mass from what it had before. It's no longer going to be m2, it's going to be equal to m2 minus dm. So this mass is going to be equal to m2 minus dm. And its velocity will also have increased in the upwards direction, because that's how a rocket works. A rocket basically works by shooting stuff out of one end, and because of conservation of momentum, it ends up gaining momentum in the other direction. So this is going to end up having a velocity of v plus dv. So now we've got the after situation and the before situation. We can figure out the momentum afterwards and the total momentum before, and subtract one from the other to get what delta p is going to be. So let's look at the momentum before, because that's easy, right? So pb for momentum before is going to be equal to m2 times v, right? P afterwards isn't that difficult, it's just a bit more algebra. So first we have to consider the momentum of the remaining rocket. So that's going to be equal to m2 minus dm times its velocity, which is v plus dv. And then we've got to consider the momentum of the tiny parcel of water that's been ejected out. And that's basically going to be in the negative direction, right? If I'm defining this as the positive, then I'm going to define any momentous this way as negative. So the momentum of this thing over here is going to be equal to minus v0 minus v times dm. So now all we've got to do is expand these brackets and see what ends up cancelling. So you're going to have m2 times v times m2 times dv times v minus v times dm. And this last term over here, because it's the product of two infinitesimally small quantities, dm and dv, that's basically equal to 0, because you're basically multiplying two really, really tiny numbers together. So I can neglect that from this expression altogether, because this approximation actually works better in the limit where dm and dv become really, really tiny and tend to 0. Now I can expand this bracket as well, and I get minus v0 times dm plus v dm. So I can instantly see these two terms over here are the same, but opposite signs, so they cancel. So I'm left with this expression over here. Now if I want to figure out what dp is, all I have to do is just do pa minus pb. So dp is going to be equal to pa minus pb, which is going to be equal to m2v plus m2dv minus v0 dm minus m2v. And this is good because we also got m2 times v cancelling, so we can get rid of that. And we're just left with this relatively simple expression over here. So now all there's left to do to get close to the answers is to basically figure out what m2 is, how m2 varies with time, and basically figure out an expression for dm. And this is kind of easy with the information we've been given. So we know that the initial mass of this rocket is going to be equal to m0. So this is the mass it has before it's even ejected any of its water. Okay, and this is and dm over dt, which is basically the mass flow rate, is basically given as r0. So logically, if we think about it, m2, if we were to make an expression for m2 as a function of time, it's going to be its initial mass m0 minus its rate of change of mass times t, which is going to be equal to minus r0 t. And similarly, dm can be basically figured out by rearranging this thing, and basically we're going to get dm equals r0 times dt. So this expression ends up becoming minus v0 r0 dt. So let's write that. So dp, the expression we have for dp now, is basically going to be equal to, we plug this into m2 over here, so it's going to become m0 minus r0 t times dv, make that closer to an r, times minus v0 r0 dt. So this is basically what we have for the change in momentum now. So if we want to get the net force, we got to divide the whole thing by dt. So dp over dt is going to be equal to this times dv over dt, which is basically the acceleration. So we got m0 minus r0 t times the acceleration of the second mass. And we basically got this thing cancelling. So dt over here is going to be cancelled, and we're going to get minus v0 r0. So this is our expression for the net force that's acting on m2. Because the string is inextensible, the rate at which the second mass accelerates upwards has to be equal to the rate at which the first mass ends up accelerating downwards. If there's a difference in the accelerations, then that basically means that the length of the string has to change somewhere along the way. And we're assuming that the string is inextensible, right? So this acceleration over here can be worked into the equations of motion for this mass over here as well. Also, another thing we know is that the tension in both of these parts of the string has to be equal. We can call that T. So based on that, we can figure out what the net force is acting on M2 over here. So F net is basically going to be equal to, well, you're going to have the tension force acting upwards, so we can put T over here. But you've also got the weight of M2 due to gravity acting downwards, right? I've not labelled that in this diagram because it would get very cluttered, but you'd also have the weight of it acting downwards. So you're going to have minus M2G. And we know what M2 is as a function of time. So basically we can get T minus, it's going to be this is going to be M0 minus R0 T times G. So now if we equate these two things, we can basically get what the tension is and use that tension to figure out what the acceleration has to be on the first mass. Because as we've discussed earlier, the tensions on both of the masses is going to be the same. So I'm going to do that on another piece of paper so this one doesn't get too crowded. So the equation of motion we have for the second mass at the moment is going to be equal to T minus M0 minus R0 T times G equals dP over dt, which is all that stuff that we figured out earlier, which is going to be equal to M0 minus R0 T times A minus V0 R0. So if you rearrange this, we can get an expression for T, which is the tension. So we end up basically getting M0 minus R0 T times A minus V0 R0 plus M0 minus R0 T times G. Now let's do the same thing with the first mass, and this will be considerably easier because that first mass, M1, is basically going to have a constant mass. So let's draw a diagram for that first mass. So this is just the first mass I'm talking about here, and it's going to have the tension force acting upwards, and it's going to be having its weight acting downwards. But usually what you do is you just balance both of these because if it was a statics problem. But in this case, you've got a net acceleration, so these won't balance. In fact, the difference of these two forces is going to be equal to the resultant force on this mass over here, which is going to be equal to m1 times its acceleration, right? So we can write the equation of motion for this. So I'm going to define this as the positive direction this time. The reason I'm defining this as the positive direction is because if you imagine the second mass accelerating upwards because of its rocket effect, then the first mass is going to be acting, accelerating downwards, right, at the same rate. So it's more natural to set the positive direction as downwards in this case than it was for M2. So if I set this as positive, then basically I'm going to get for the net force is going to be equal to M1G minus T equals M1 times A. Now all we've got to do is plug this big expression over here into the tension and rearrange a bunch of stuff to figure out what A is. So let's do that. So this is going to become M1G minus M0 minus R0 T times A plus V0 R0 minus M0 minus R0 T times G. And that's all going to be equal to M1A. So we want to figure out what A is, right, as a function of time. So let's just take all the A terms to this side over here. And we're basically going to get on this side M1G plus V0 R0 minus M0 minus R0 T times G equals A times M1 plus M0 minus R0 T. So now we can collect all of the R0 terms on this side. So if we collect all the R0 terms, we're going to get R0 times V0 plus GT. And if we collect all the terms that are common with G, we're basically going to get M1 minus M0 times G equals A times M1 plus M0 minus R0 T. So that's it. All we got to do is just divide this whole thing by this expression and we get the acceleration as a function of time. And that's basically going to be equal to R0 V0 plus GT plus M1 minus M0 times G divided by M1 plus M0 minus R0 T. So yeah, that's the expression I got for the acceleration as a function of time. Really interesting problem because it's basically taking a classic pulley problem and adding a bit of spice into it by putting a rocket on one end.